due to a point charge is given by some proportionality constant multiplied by the charge over the distance. I'll tell you more about that in a second. But let me just tell you up front here that the potential is a scalar quantity that could be positive or negative depending on the sign of the charge, because everything else is positive. And the SI unit for this physical quantity is called the volt. It's named after the Italian scientist Alessandro Volta. And we'll see later when we talk about the relationship between the potential and potential energy is that the volt is defined as 1 joule per 1 coulomb. So 1 volt would be 1 joule per coulomb. 1 joule, which is the unit of energy, divided by coulomb, which is the unit of charge. Now let's talk a little bit about this proportionality constant. K can be written as 1 over 4 pi epsilon, and there's a reason people write it as K because it's a much easier representation. But you should know that it's 1 over 4 pi times epsilon, where epsilon is known as the permittivity of the material. So remember when I told you this depends on the material. 1 over 4 pi epsilon. Epsilon is the permittivity of the material, known as the absolute permittivity, and that depends on the material. And the absolute permittivity is equal to kappa times epsilon naught. Kappa is called the relative permittivity, sometimes called the dielectric constant, even though this kind of language is kind of dying now. People prefer to use the term relative permittivity, but if you read some older texts, you'll definitely see this dielectric constant mentioned. So the absolute permittivity then would be equal to the relative permittivity, or the dielectric constant, multiplied by the permittivity of free space, epsilon naught. So that's the base one, and that's given by 8.854 times 10 negative 12 coulomb square per newton meter square. And if you think about air, for example, if you go and look up the dielectric constant of air, relative permittivity of air, it's about 1.0006. So for air, for example, the permittivity is really quite close to the permittivity of vacuum, so we don't even worry about it. We just say it's the same as the permittivity of vacuum or free space. And like I told you, people like to write it in terms of K, not in terms of epsilon, because 1 over 4 pi epsilon naught turns out to be a really simple number, which is 9 billion. 8.99, to be a little bit more precise, 8.99 times 10 to the 9 newton meters squared per coulomb squared. So for example, if you want to calculate the electric potential produced by some point charge, let's say 3 microcoulombs, at a distance, let's say at 2 millimeters, then you would plug in right away. Simply you'd say, okay, the potential at some distance r due to some charge q is given by k times q over r. And since I didn't mention any kind of material in here, then I'm just going to take it to be vacuum. And I'm going to say it's 8.99 times 10 to the 9, that's the K, times the charge, 3 microcoulombs, so that's 3 times 10 negative 6 coulombs, divided by the distance, which is 2 millimeters. And if I work it out, that gives me 13 million volts. You could also think about sort of if things are not explicitly given in terms of the charge and the distance, you could calculate the distance yourself. So suppose I have a charge here that is sitting here. In this case, let's say it's 8 nanocoulombs. And here's a coordinate system xy that I made up to be able to represent the distances between things. I know, for example, where this charge is located. It's located 0.5 meters in the x and 1.5 meters in the y. And then I know these other points, P1 and P2, where they're located. I can calculate the potential at each one of these points. So at P1, I would say the potential then is given by KQ over R. And R here is the distance between the two locations. And I can calculate that by figuring the difference in the x component and the difference in the y component. And of course, using the Pythagorean theorem, I can find the distance between the location of the charge and the location of P. So the critical piece here to understand is that this R that appears in the equation, V equals KQ over R, that R is the distance between the charge and the point. And you can calculate that in any number of ways if you know where the charge is located and where the point at which you want to calculate the potential is located. So for the case of P1, I know that I go 6 squares in x and 2 squares in y, and each square in half a meter. So I can figure out the distance between them as the square root of 6 times 0.5. That's 3 meters to the right, and then 1 meter in the positive y, and then I square each. I take the square root, calculate the potential, turns out to be 23 volts. If I want to think about the point P2, I say, okay, hang on a second. For P2, because it's 2 squares in the x and 2 squares in the y is the distance between the charge and the point, I can think of it as 1 meter and 1 meter, and I can calculate the potential at point P2 to be 25 volts. Now, what if I don't have just a single charge? What if I have multiple charges? How would I calculate this? Turns out because it's a scalar quantity, the story is really quite simple. Because you say the potential at any point P, due to a bunch of charges Q1, Q2, Q3, all the way to Qn, all I need to know is how big the charges are, their magnitudes and their signs. So positive, negative, how many coulombs on each one of the charges. And then I also need to know the individual distances between each of the charges and the point P. Notice that the direction is not important at all. This Q1 could be at any other location that is a distance R1 from P, and I would still get exactly the same potential at P. And the potential then at the point P would be the sum of the contributions of each of the potential from each charge. It's called the superposition principle. But because the potential could be positive or negative, you got to pay attention to that sum because each one of the charges could be positive or negative. So each one of these terms could be positive or negative. And when you're summing things over all of the different charges, you got to keep the sign. So you calculate the contribution due to each one of the charges. So you say KQ1 over R1. So KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3, etc., all the way to N. So this here is a sign that indicates the sum over the index I that runs from 1 to N. So I here runs from 1 to N, so I get KQ1 over R1 plus KQ2 over R2, and so on. And that gives you the potential at any point. So for example, suppose I'm thinking about this configuration A up here. I have some charge positive Q separated from some charge negative Q by a distance A. By the way, we call this a dipole because it's two poles, two charges that have the same magnitude but different signs separated by distance. It's called a dipole. Suppose I want to calculate the potential at point P that is another distance A to the right of that negative charge. How would I do it? Well, I would calculate the contribution from each one. So I say the positive charge is separated from that point P by twice A. That's the distance from the charge to the point P. So I say K times that charge over twice A. So this is the contribution from the positive one. And then the contribution from the negative one is K times the negative Q over the distance from the negative Q to the P, and that distance now is A. So the positive charge is separated by distance twice A, but the negative charge is only separated by distance A. And then if I do this algebra, then I get this potential at point P is negative. It's very important to pay attention to the sign because the positive charges create positive potential and negative charges create negative potential. For the configuration B, separate configuration, now I'm thinking about two charges that are equal in magnitude and sign, separated by some distance A. And then I want to find at the point P how big the potential is. So notice that the distance between the two charges really in this case doesn't matter at all. All that matters is the distance between each of the charges and the point P. So I say charge 1 has a magnitude of Q and a positive sign, so I get K Q over A, and the second charge also the same thing, and it's separated by the same distance, so and the direction doesn't matter one bit because this is a scalar quantity. So I get 2KQ over A. For this last one, if you sort of look at the symmetry of the situation, you might be able to figure it out right away. You say the positive charge and the negative charge are the same distance away from the point P. So I can take this part, I can take this idea here and do the two positives and do the two negatives. But I can also think, oh, look, this positive and this negative are the same distance away from the point P. So whatever potential this one creates, this one is going to create the negative of it. And whatever potential this one is going to create, this one is going to create the negative of it. So I'm going to end up with zero potential. But if you want to work it out, you say the positive Q times the distance, which if you work out the Pythagorean theorem, you find that this is A over square root 2. And then the contribution from the other positive charge, and then the contribution from this one negative, from this one negative, you add it up, you get zero charge. Now, I like to think about sort of representing this potential in 3 dimensions. I like to think about how it's represented in my mind so that I have a sense of, when I'm thinking about these things, I have a sense of what the potential landscape looks like. So for example, in this kind of simulation, if I turn off the electric field, let me put the grid on, and then I'm going to turn off this thing called the voltage. And the voltage is another name that we give to something called the electric potential difference. Or you can say the voltage is another name we give to the electric potential. And if I put any charge, 1 nanocoulomb, let's say, this particular simulation represents the electric potential by this glow. But I can also use this with the crosshairs. I can put it at any location, and this measures the potential for me. So this would be 18 volts, for example, at this particular distance. So if I know that this is 1 nanocoulomb, and I can come and measure the distance between these 2 points, so I can put this right on where the charge is, and then I stretch this to any point P that I care about. In this particular case, because I'm thinking about this crosshair, and I can put it here and say, oh, it's 50 centimeters away, so that's 0.5 meters. So K times 1 nanocoulomb over 0.5 meters gives me 18 volts. I can also put it at any other point, and I can go and measure the potential at that point. Notice, for example, if I put it here, let's say, and then I'm just going to put this away for a second. You'll see, for example, it's at this particular distance, it's 6 volts because this is positive 1 nanocoulomb. What if I put another positive 1 nanocoulomb on top of it, right on top of it? So that means this charge now is positive 2 nanocoulombs. So it gives me 12 volts, double. And what if I put negative 1 on top of it? That shields one of the positives, so I get back to the 6. And if I put another negative 1, that's neutral now. Look, no potential anywhere, it's 0 volts everywhere. Okay? So that's how this particular simulation represents the electric potential. This one here represents the electric potential by these lines. And you can see for a positive charge, for a negative charge, negative 1 nanocoulomb, this is what it looks like. If I put one of those dipole things that has positive and negative, and let's say I want to show a Y slice, and then you can move it around, you can see what the electric potential looks like at different points. And we'll talk about this representation in a second. Here's another way of representing things in which you just take a slice in that XY plane, so that would be a Z slice, and then you put that third dimension to be the potential, and then now you can plot the potential based on the location and the sign of the charges. So right now, both of the charges are negative, so you can see these sort of holes in the fabric of that potential, or you can sort of turn one of them into positive, so you can see how the potential changes in that landscape. If both of them are positive, this is what it looks like. So that's another representation of the potential. So notice that the common thing is that the potential is a physical quantity that has value over all space. And that's very important to recognize. Another way of representing things is through something called an equipotential surface. So it uses this kind of analogy to topology. Is that instead of representing things with this sort of three dimension, I can project it down onto the plane and talk about these contour lines, which are lines that represent heights. Put all the points that have the same height. And for electric potential, it would look something like this. So I can play with how big the charges are, and I can go and look at the electric potential view, and I see the equipotential view, and I can see all of these lines, and each one of these lines indicates that it has all of these points have the same potential. That's called an equipotential view. And in this particular simulation, the way to find this equipotential view is to put charges around here. Let's say I have a bunch of charges like that. And then I come in here and I say, I want to find the line of equipotential that is 14 volts. So I find a point that is 14 volts. I click on this pencil. It draws that equipotential surface. All of the points on this green curve here are points that have potential of 14 volts. And that is what these lines are. They're called equipotential surfaces. In this particular simulations, these curves are the intersection of the equipotential surfaces with the chosen plane. The most important quantity, really, when you're talking about electric potential, is the electric potential difference between 2 points. All of our instruments have these 2 ports, and each port will be connected to a point, and they measure what we call the electric potential difference between these 2 points. And that's given by the potential between the potential at some point minus potential. So the way we say it is that the electric potential difference between any 2 points in space A and B is given by VB minus VA, because I'm thinking about starting and ending. So I started A and I ended B, so the change in potential would be VB minus VA.